Welcome to part 2 of the section 8.4 matrix inverse video. I'm going to go ahead and flip to page 2 of the notes here. We're going to get started with this example problem. These problems are brought applications of matrix inverses. So on the previous video I showed you how to find an inverse, and now I'm going to show you what the heck we can do with them. Don't forget, your calculator is way more efficient than you are personally at finding the inverse of a matrix. So anytime you're working on one of these, you should check your answer with your calculator, see if it makes sense. Okay, so I've given you two matrices here. I've given you this matrix, and I've given you matrix E, and then I've given you its inverse. I'm not going to make you find its inverse. This one would be pretty tedious because it is a 3 by 3 matrix. But what I want you to do right now is I want you to compare matrix E with this system of equations right here. I want you to pause the video and compare those two to see if you notice anything. Go ahead and pause it now. Did you pause it? I hope so. And I hope what you also noticed is that matrix E represents the coefficients on the variables in this matrix. Notice how 1, negative 1, 1 matches up with x minus y plus z. 0, 1, negative 2 matches up with 0x plus y minus 2z. So what on earth can we use this for? Well, this system of equations right here is going to be very similar to the following. Matrix E times matrix X equals matrix B. We've done, I showed you something like that on the front side of the paper, and now what am I going to do to show you how to do an application of matrix inverses? Well, if I write out this matrix equation, it's going to look like this. I'm going to have matrix E and then I'm going to multiply that by matrix X, which is my variable matrix. 3 rows, 1 column, which represents my variables. And that's going to equal the constant matrix, or the constants from my system of equations right here. So in order to solve this system, I can multiply both sides of the equation by E inverse, and that'll give me the matrix X all by itself. So the left-hand side, if I multiply by E inverse, will just be XYZ. And the right-hand side, notice the order. Matrix multiplication, the order matters. So I need to multiply E inverse by B. That's E inverse, and I need to multiply that by B. So I want to pause here for just a second to kind of give some of you a chance to catch up. This system right here, I have rewritten as matrix E times matrix X equals B. E is the coefficients, X is the variables, B is the constants. Well, from what we did in the part 1 of this video, I know that X equals E inverse times B. If this system has one unique solution, then E has to be invertible. I showed you right here that E is invertible by giving you its inverse, so that must mean that this system has a unique solution. I'm pretty excited to find that solution, so I hope you want to jump right into it with me. Let's go ahead and start by writing out that matrix X. And now what we're going to do is we're going to do matrix multiplication. And I'm going to go ahead and do some color coding here so you can follow along. First, I'm going to do that row by this column. And that's going to give me 8 minus 5 plus 1. Next, I'm going to do this row by this column. And that's going to give me 0 minus 5 plus 2. Last but not least, we're going to do row 3 by this column, and that will give me 0 plus 0 plus 1. Let's go ahead and simplify these values. I have 4 for 8 minus 5 plus 1. 0 minus 5 plus 2 is negative 3. And 0 plus 0 plus 1 is 1. And what do these values represent? 4 is x, negative 3 is y, and 1 is z. Fascinating, folks. Give yourself a little pat on the back. You just did your first application of a matrix inverse. Okay, let's move on. Let's look at example 2 for applications of matrix inverses. And this one sounds like Mr. Vass is blending Skittles again. I know Mr. Vass pretty well, and to be honest with you, he's not even a big fan of Skittles. He was just trying to pick a candy that's got different colors. This is a made-up problem. It happens to be very similar to one of the applications in WebAssign, so you might want to pay close attention to this example before you get into the section 8.4 WebAssign. Okay, back to the problem. Mr. Vass blending Skittles again. He still has the same 3 colors as before, red, green, and yellow. However, the colors are not blended this time, so he's got a bucket of red, a bucket of green, and a bucket of yellow. He wants to make a 30-pound blend that has a total cost of $100. He buys red for $4 a pound, green for $2 a pound, and yellow for $1 a pound. He also wants to have twice as much yellow as green in the final batch. So most of you read that word problem and then just decide, maybe I'll just take the F. Maybe it's not that bad because I have no idea where to start. But what I've done for you here is I've tried to show you a step-by-step approach of how to set this problem up. The first thing we're going to do is define the variables that we're going to use in this problem. This problem requires 3 variables. I've defined them as R, G, and Y. Red is going to be the weight of red Skittles, and that's going to be measured in pounds. G is going to be equal to the weight of green Skittles, that's also going to be in pounds. And Y is going to be the weight of yellow Skittles, also in pounds. One of the things that I've noticed students struggling with is just actually defining variables in one of these application problems and picking the units. Sometimes you think it's dollars per pound, sometimes you think it's dollars, sometimes you think it's pounds. But in order for me to make a 30-pound blend, in order for me to make a 30-pound blend of these Skittles, I need to know how many pounds of each. So that's how I determine what each variable is going to represent. Now let's move on to the system of equations to model this problem. The first thing we know is we have a total weight requirement. And the total weight we are told is 30 pounds. So that means R plus G plus Y equals 30. That's going to be equation number 1 in our system. The second thing we know is we know what we want the total cost to be. We want the total cost to be $100. Well, in order to get the total cost, we need to multiply the weight of each color by its associated cost. So red is $4, so $4 per pound times the number of pounds in red is going to give me, sorry about that, folks, slight technical difficulty, take 2. So $4 per pound times the number of pounds will give me the cost of the red Skittles, plus $2 per pound for the green Skittles times the number of pounds of green. Finally, plus $1 per pound times the number of pounds of yellow Skittles, and that is going to be my total cost equation. The third equation is going to be the toughest for you as the student to come up with, and I'm going to call this the yellow-green restriction. So here's how I'm going to word that. The last sentence of the problem dictates this final equation. So I'm going to go ahead and highlight those both with yellow. It says, Mr. Vass also wants to have twice as much yellow as green in the final batch. So if he has twice as much yellow as green, that means he would need to double green to equal yellow. Okay, don't write that down just yet because I'm going to erase it, and I'll tell you why here in a second. First of all, I want you to think through the logic behind that. If he wants to have twice as much yellow as green, that means you have to double the green to equal the yellow. Now that you've had a chance to think about that, think about why I can't leave the y on the right-hand side. The reason why I can't leave the y on the right-hand side is because we have to have all the variables on the left and all the constants on the right. So in order to do that, I need to subtract y from both sides. And when I subtract y from both sides, what I'm left with is 2g minus y equals 0. And this is worth talking about. Okay, so I'm going to write a little note for you here. All right, this note includes everything that I just mentioned here. If you have twice as much yellow as green, then 2g equals y. If you solve for 0 on the right-hand side, you get 2g minus y equals 0. Okay, we're ready to move on to part C of this problem, which is to transform this system of equations into a matrix. And we're going to do that as follows. I'm going to start with a 3x3 matrix of my coefficients. Top equation I have r plus g plus y. And that's the coefficients of my variables. My second equation is 4r plus 2g plus 1y. And my third equation is 0r plus 2g minus 1y. That I'm going to call that matrix A. And the next thing I'll need to add is a matrix for my variables, r, g, and y. And I'm going to call that matrix X, capital X. And that has to equal my constant matrix, which is the constants from our system of equations. And we're going to call that matrix B. Folks, the hard work is done. Setting up that system of equations, transferring the word problem into algebra is the hard part. The next part is we're going to use our calculator to determine the inverse of our coefficient matrix, and then use that inverse to solve the problem. Well, what do I mean by solve the problem? We're going to have x equals A inverse times B. And from your calculator, you should be able to get A inverse. I'm going to go ahead and write it out for you right now. Okay, folks, here's A inverse, which I got from my calculator, and I'm now going to multiply that by the matrix B, which is all the constants from my system of equations. And that results in the following solution. 45 halves for red, 5 halves for green, and 5 for yellow. Because this is an application problem, I would probably report each of these values as a decimal. And this is going to be 22.5 pounds of red Skittles, 2.5 pounds of green, and finally 5 pounds of yellow. I hope that you have enjoyed this video, both parts 1 and part 2. Say goodnight to chapter 8 because she's done.